In the previous section, we created a transfer coefficient matrix by running a unit source dispersion calculation for each emission period over the entire period of interest. This approach is best for historical simulations. During a real-time event, HighSplit can be configured to provide a continuous update to the TCM with each new forecast cycle by first initializing the simulation with the pollutant particles valid at the current start time. These particle position files would have been written at the end of the previous simulation. For example, if we want to do daily updates for a multi-day simulation, at the end of each day, HighSplit writes a file of particle positions. The position file is read at the start of the next day's calculation. The point of this segmented approach is that in a real-time situation, as the emission event continues, it is not necessary to go back each day to the start of the event, but one can start a new simulation each day with all the previous release particle positions, a considerable saving in computer time for long-duration release events. To simplify the example, only one meteorological file is used, and the output files will be written and restarted every 3 hours. Naturally, if this script were to be customized for other applications, the restart interval and the concentration file output interval do not need to be the same. Except for the new script tcm_make, the input files required for the simulation are the same as the previous example. In this case, all simulations are divided into 3-hour segments. For example, if the first emission starts at day 14, hour 0, that simulation would end at day 14, hour 3. At 14:03, we start a new emission to end at 14:06, but also continue the 14, hour 0 emission to have it end at 14:06. Every 3 hours, we would be running an additional simulation. The file name convention is by release start time and the start time of the concentration output. Particles are only released during the initial simulation. A restart simulation has no new emissions and only continues with the particles released during the release phase calculation. To perform this type of calculation, the particle position file par_dump must be written at the end of each simulation by setting the namelist variable ndump equals 3. Each day-hour loop of the script contains 2 HighSplit simulations, and therefore a customized control file must be created for each one. The first simulation is a restart of the previous simulation. Restarts are based upon a list of release start times in the start_list.txt file. For a restart, the emission rate is 0 and the particle initialization file par_init is read, which is the particle output file from the previous calculation for that start time. The second simulation is a new release for that start time, where the release rate is set to 1 for a 3-hour duration, and the release time is added to the start_list.txt file. After each simulation, the particle position output file par_dump is renamed with the release start time as a suffix to the name. Prior to a restart calculation, but not a new release, the par_dump file for that release time is renamed to par_init, the HighSplit default name for the input of particle positions. Go ahead and start the script. After all the HighSplit runs have been completed, you will have 300 files starting with the CG name in your work directory. There is one file for each release time and output period. The post-processing steps are similar to the last section, except for the addition of a new component to merge the CG files. The con append program is used to merge the 300 files, which represent 24 release periods, into one file per release period that contains all the output times. This is accomplished using a wildcard test to find all the sampling times for a release, and then con append merges those files into a single TG file containing all the output periods for that release. The TG file contents are identical to the TG files created in the previous example. Air concentrations and depositions for a unit source, one file per release time. Therefore, the subsequent post-processing steps are identical, using con decay to add the emissions and decay, and con merge to add together all the release times into one output file. This section described how a transfer coefficient matrix can be computed incrementally as the release progresses, updating the particle position from previous releases with new meteorological data. After an update has completed, if desired, another simulation can be conducted using forecast meteorological data. In the next section, we'll be computing dose with multiple radionuclides.